that's the end of simplex method. We want to talk about the next topic. Dual problem. Okay. Sometimes we have this minimization Cx and subject to x greater than or equals to b and x greater than 0. Okay. Sometimes we call, suppose I give you this kind of problem, ask you to solve for that. Initially, we'll call this as a primal problem. And if you find this one is tough to solve, maybe I will transform them to its dual. And its for dual becomes suppose sometimes I will give you this kind of problem actually to solve it. And so if I give you this kind of problem, we call it primal problem. And you try to transform them to dual. Okay, so it's not easy to say, okay, the maximization problem is a primal problem and the dual, the minimization is a dual. No. The primal problem is the original problem I give you. And I try to find its dual to find. Do they have some similarity with some property? Okay? So in the following, we'll talk about, sometimes we'll focus on minimization problem. Sometimes we'll focus on maximization problem. Like a simplex method, we utilize the maximization problem to talk about, to explain the simplex method. Okay? So in the following discussion, probably sometimes we'll utilize the minimization, sometimes we utilize the maximization. Okay? But usually, sometimes it doesn't care about which one is primal, which one is dual. Because when I give you this kind of problem, I try to find the dual. So you get this problem. And if I find the dual of this problem again, it will go back to the original one. Okay? So the primal or dual actually just try to mark which one specific. Okay? So the property of this I will explain that how can I transform them in the end. Right now we just talk about start from the property first. You learned the operations research before, so you also see this kind of property. So I try to utilize a different way to explain duality. Okay. So as we know, the primal problem we can find the dual, and the dual of the dual problem goes back to the primal problem. So usually they should have subproperty. If we can find y, we can find the x. For example, if I find the x bar is the optimum for the primal graph, there will exist. There exists the y bar. That would be feasible for here. I didn't say y bar is optimal. I only say I can find it's feasible. A feasible solution is such that the c x bar when the x bar goes put into the z value is equals to when I put the y bar into the subjective function value. We will find these two values the same. So as you know the dual duality before, you know that if it follows that y bar actually is optimal solution. Okay, but here I will start from this. I will say that's feasible. And finally, we will find it's an optimal solution. And during this process, we want to prove that this y bar is an optimal solution. Okay? You already know that, but during this process, during the following discussion, we will check. Okay? Okay? And actually, in the following discussion, we will find, we will have some discussion. Say x bar is feasible in the primal form. Based on this constraint, we can find a feasible region, right? And the solution inside the feasible region is actually a feasible solution. And I can find any feasible solution from this constraint. And I also can find another y. Feasible solution y based on the constraint. And if we find them. Then we can guarantee the x bar and y bar is the optimum solution. That's the following discussion. And that's you already know. Okay? But we just start from what you already know. Okay? So that's why that's the following topic, duality. Okay. You also know that if I give you a primal problem, you can transform it to its field, right? Because you already know. All of you should learn the operation research before, right? You measure. You didn't learn the up. Are you sure? Business administration, but in the school, business administration, they have to learn one semester operations research.
No, they can choose, but they are not.
气管 business admin. But in the school, the business, you didn't learn the. So no. Let me tell you the story. Long time ago, business probably maybe 10 years ago. Business administration, they have operations research. They have this course, but they don't have teacher to teach them. So the class is taught by the teacher from INA. So long time ago, I teach that class before. But after that, probably we don't want to support them. So they just say they limit because they cannot explain it. We have video. I can tell you the story. study here and continue to the PhD. So you have many experience here, right? So why you still choose here? You don't want to choose goes to the other school. Say again? Why? So you want to continue to PhD? Oh, you. Sorry. So who is your advisor? We only have one Soros. Doesn't he give you any suggestion about Soros? Sometimes in the class I will talk about something, but because we have video here, so they will be uploaded to the YouTube. So I cannot say anything. Okay, you all know how to transform the primal problem to a dual problem. But question is why? Why we do that? And you all also know the process, but how do we know the reason? You also only knows that okay, I just changed the position from the objective function coefficient to the right hand side. From the right hand side to objective function coefficient. And then I transpose. Hey, everything is done. The question is why? Why we do that? Okay, so the following is the example to show you like why we want to do that. Suppose we have this kind of questions. So right now, I give you a maximization problem. Then what I say it is a primal problem. Okay? Okay. Suppose I want to find the optimal solution of this problem, but I don't want to utilize the simplex method. Do we have another method to find it? So then, and suppose Z bar I didn't find it yet, but I can suppose Z bar is the optimum value of the primal problem. And as far as I say, I don't want to utilize simplex method to solve this problem, but can I utilize another discussion? Maybe some method, try to find Z value. Okay? So the duality theory is the motivational duality theory is that when we work in on the simplex method, you will find okay, that's a cool way, and because based on that, I can find optimal solution. But if the problem is too huge, simplex method sometimes is too takes a lot of time. So someone will try to find another way to discuss it. Okay. So let's continue. Right now, we still don't have any idea. So, for a feasible solution, x1, x2, x3, and I plug into this objective function, let's I plug in the x1, any feasible solution x1, x2, x3 into this objective function, and I got the value. And I say z bar is a optimum solution. That's smaller than or equals to. Because maybe I'm very lucky. I already find a feasible and also an optimal. Okay. So for any feasible solution plugging into this objective function, we can call this value as the lower bound of the optimum z value. Okay. So any feasible solution, when I plug in, I will find a value, and I already know that it should be less than or equals to z bar. So every value plug in, I will find that that's the lower bound. Okay. Means that. Right now we already have a lower bound, and I don't have an upper bound of that. So the reason is that we try to find the upper bound. Okay, for the maximization. For a maximization problem. In the very beginning, we will try to find it is from, suppose, for this problem. When I transform them to standard form, the initial solution or initial value of z, we start from 0, right? And for the iteration by iteration, we will increase the z value until we got the optimal solution. That's what we do. Okay? So here we say the lower bound. This means that for any feasible solution will provide me lower bound and lower bound. Okay? But probably don't care about that because in the very beginning you say, I already have a simplex answer. I apply them once. I will get optimum solution. Yes. Currently, yes. But in the future, probably not. You work on your research. Right now, how can we construct the upper bound? Is that we transform them to the field. And I got a field. Oh, this one's prime. The prime one is a maximization problem. The dual actually is the minimization problem. So minimization problem is that we start from very, very large value and we try to apply them and try to decrease the value and goes to infinity. Goes from infinite value to optimal value. Okay. So another story is that go back to this discussion. Again, like this one, I can choose any feasible solution from the dual, and maybe it is not optimal. So it can give me a value which is greater than the optimal value. So that's why here will become for the lower bound and upper bound to you would be, say, let's don't care about it because I can find the optimum solution. But in the future, when your problem is too huge, too complex, you cannot find the optimum solution. For the primal problem, you can find the lower bound only. Okay? But if without this upper bound, and you stop at this lower bound, you don't know how good the lower bound, how close to your lower bound to the optimum solution. Okay? So in that way, I will transform them to another problem. And again, because it's a complex problem, we still cannot find the optimum solution, but we can find upper bound. So once we can find lower bound and upper bound in a limited time, even I cannot find optimum solution, I will know that the optimum solution will be located between. Okay? So at a time, if we find lower bound and upper bound are very, very close, then we know that we are very close to optimum solution. But if they are very large, we're in trouble. We have to find another way. Okay? So one day, when you work in your research, probably you only can find it. There's no way you can find optimum solution. There's no way. Sometimes, because the real problem is too complex, there's no way. The only way you can find it is maybe based on any meta-heuristic algorithm, probably. And how can you guarantee, or how can you make sure your solution is good? Sometimes the easy way is you try to compare to the other persons. So okay, my solution is better than the other persons. So my solution is better. Yes, probably you can say that. But in most cases, sometimes we will just do to construct the upper bound. To tell them how good my solution is. Okay? But sometimes it's not easy. It means that you have to solve two problems. Originally you only have to solve one problem. So that's the purpose of the dual problem or duality. Okay? If for every problem I can solve for optimum solution, then we don't need to do that. But in the real world problem, sometimes too complex, I cannot find optimum solution. So we need this this rule or this property help us to find how good the solution is. Still need that. I still need that. I didn't finish that. Suppose you still can see it. I have objective function. I have the objective function, right? And I have two constraints. Okay? And then I mark the first constraint as 1. The second constraint is 2. Okay. So let's continue. Suppose you still can see that. We multiply the first constraint by 20. So we get if we multiply the first constraint by 20, you got this, right? Okay. And our objective function, our objective function is 60x1 plus. This is our objective function. This one is our objective function. Tell me that. What is the relation between this black one and blue one? Say again? I mean compared to right? Why?
One is non-negative.
X1, X2, X3 are non-negative. So we have a larger coefficient. So this, the black one is greater than equals to blue one. Okay. So what does that mean? It means that our objective function value is less than 960. So here we can try to construct the upper bound. Okay? Okay. But it's still not good enough because 160 is much larger than 60. 120 is much larger than 30. Because we want at least we need this. Okay? So it's not, yes, that's our upper bound, but it's not good enough. So we try to do construct another upper bound. And the next problem is that we multiply the first constraint by 10 and second constraint by 10. And then L is 2. L is 2 inequalities. Okay. Individually we multiply the first constraint by 10, second constraint by 10, and we add it together. If it comes so compared to our objective function, 60x1 equals 30x2. So 680 is another upper bound. It's much smaller than 960. Okay, so we have a better upper bound. Okay, but again, if we only because we don't know the optimum solution is, so we still don't have any idea how good the upper bound is. Okay? So do we have another way to construct the upper bound? That's the idea. So we can try to mimic this scenario. We have a lower upper bound. We can multiply different constraints by different values. So we choose y1 and y2 as a multiplier for constraint 1 and constraint 2. And they should be greater than or equals to 0. Okay. So if we do that, we will find that the right hand side will become that's the right hand side of the first constraint, right hand side of the second constraint. Okay. That's the first constraint, x1's constraint coefficient. That's the second constraint. Okay, and multiply by 1, and y2. So this synchronous. You can treat that the y1, y2 as not variable. It's a multiplier, just like this 10, empty of 0 value. The variable here is still x1, x2, x3. And I want to compare if they are really greater than or equals to 60 x1 plus 30 x2 plus 20 x2. Right. Like the first upper bound and the second upper bound, I need this relation. So that's why we say, okay, this one is the upper bound. Okay. So how can I know it is true? How can I know I construct this upper bound? First of all, I have to make sure the value value. Say again. What is positive value? Here, y1, y2 is greater than or equals to 0. So we already know y1 greater than 0, y2 greater than 0. Okay? But we want to do a comparison. We say we want to find the upper bound, and then this upper bound should be greater than or equals to this one. So I have to compare these two, right? Just like here, I need to compare. 160 should be greater than or equals to 60. 120 should be greater than 30. Okay? So, right. So how how about the coefficient of x2? 6y1 plus 2y2. And y1 plus 5y2. Okay. Okay. Okay, any questions? Right. Again, that's a discussion. Initially, I construct two constraints, two upper bound. But when I construct these two upper bound, we don't know how good they are, and also there's many choices of this multiplier value. Okay, so we try to find a systematic way. Again, we still try to find upper bound, but we try to find the upper bound is closer and closer to z value. Okay? Right? Just like assume we still can see this figure. Maximization will prove that, will increase that. For minimization, I want to construct an upper bound close to z value. So I want to find this upper bound smaller and smaller. So the objective function is that minimize. That's the upper bound, right? We want to minimize. Do you see anything? Do you see something? Do you see something? When I say minimization, and you have these constraints, do you see something? Want to minimize this objective function. We have these three constraints, we also have these variable constraints. So it becomes dual problem. Originally I have a primal problem, right? The break one, I say that's maximization something. Okay. And long time ago, if I ask you to find a dual problem, you can write me this directly, immediately, properly. But here I just tell you the reason. How can we and why we need this dual problem? Okay, the reason is that we try to construct the upper bound. When we try to minimize the upper bound, then we get find dual problem. Okay? Great. Okay. We have a break. We call this three constraints. We will give you the mark. And for this, give you that's for the following discussion. After the break, we will have discussion. We want to talk about what is the relation between this dual problem and the original primal problem. Okay. Have a break.